You stand on the edge of Hudson Yards and look down, you won't see ground. You'll see steel, concrete, and 30 active rail lines with hundreds of Long Island Railroad trains barreling through every single day. This is West Side Yard, a rail depot that for decades was a black hole right in the heart of the world's most expensive island. There was nowhere to build because there was nowhere to sink a foundation. But in New York, they say, if there's no land, we'll make it. That's how the most expensive private development project in US history was born. $25 billion. This is Hudson Yards, a city hanging on steel threads above an operating railroad. Let's go check it out. Picture this. You need to build an entire neighborhood. Office towers, parks, shopping centers, apartment buildings. But you can't stop the trains running underneath. You can't just pour concrete everywhere. You have to build a roof over the depot that can hold the weight of an entire district. To pull this off, engineers had to create a platform. But this isn't just a slab. It's a titanic engineering masterpiece held up by 300 concrete columns, driven right between the train tracks. There was zero room for error. A deviation of a few inches would mean a column landing right on the rails. But the columns are just the support structure. The real heroes of this story? Steel trusses. When we say beam, we usually picture something a couple of workers can lift. Forget that. For Hudson Yards, they fabricated the largest steel trusses ever seen in construction. One of these beams weighs 100 tons. That's like 3 fully loaded semis, or 20 adult elephants, concentrated in a single piece of metal. These trusses were manufactured at specialized plants and delivered to Manhattan at night, when the city sleeps. And it's exactly this plant we're heading to today. When the giant crane starts lifting the 100-ton truss, you hear the steel cables pulling tight. It's the sound of high tension. The air around you seems to thicken. The crane operator works with the precision of a surgeon. The beam has to be lowered onto the caissons, so the gaps don't exceed millimeters. 100 tons of steel glides smoothly over the train sitting below. One wrong move, and billions of dollars, plus the safety of New York's entire transportation system, go down the drain. When the beam finally settles into place, the welders and riggers get to work. You see sparks flying from 10 stories up. Each beam is secured with bolts the size of a human head. But here's the secret. Since the railway below keeps running, the platform is constantly hit by vibrations from trains. If it were rigid, it would just crack. So Hudson Yards breathes. Built into the structure are giant shock absorbers and hinges that let the metal skeleton shift a few inches, soaking up the energy from the railway chaos underneath. There's heat here too, but it's the heat of glowing metal and welding torches. Even in winter, when icy wind blows off the Hudson, it's warm near these beams. They hold the energy of construction. Once all the beams are in place, they pour a concrete slab on top. That's how you create new ground. On this steel base, they planted over 200 trees and thousands of plants. But there's a catch. Tree roots can't grow deep, because down there, beams and trains. Engineers created smart soil. Under the park runs a complex cooling system. Why? Because the trains below put out so much heat that tree roots could literally cook. The Hudson Yards platform is a giant air conditioner for a forest hanging over an abyss. Sounds like science fiction, but the trees in Hudson Yards Park live in a refrigerator. Because dozens of diesel locomotives operate below, the platform heats up intensely. To keep the tree roots from cooking, a network of tubes circulating liquid is embedded in the concrete slab, drawing away excess heat. The soil itself isn't just dirt. It's a complex mix of sand, porous minerals, and fertilizer that weighs 30% less than regular soil, so the beams don't buckle under the weight of the forest. Today, Hudson Yards is gleaming glass towers, luxury boutiques, and the famous vessel installation. Tourists snap selfies, never suspecting that right beneath their feet, hidden under layers of concrete and granite, a steel army holds the line. You'll never see dumpsters or stinking garbage trucks on the streets of this neighborhood. Underground, there's a system of vacuum tubes. You toss a bag into the chute, and at over 40 miles per hour, it gets sucked by a powerful airflow straight to the central waste collection terminal. This frees the streets from traffic jams and rats. Those same 100-ton trusses are the atlases of our time. They don't complain, they don't get tired. They just carry $25 billion and architects' dreams on their shoulders. I've already told you so much about the benefits of these beams, and now's the perfect time to see how they're made. So you're coming on this journey with me right now. Manufacturing beams for Hudson Yards is a challenge taken on by only a handful of plants in the US, including Banker Steel in Virginia. Regular construction steel won't cut it here. When you've got a multi-billion-dollar skyscraper standing on your shoulders, you can't afford a single micro crack. In a massive cauldron, liquid iron boils at temperatures exceeding 2,900 degrees Fahrenheit. Precise doses of vanadium are added, along with what seems like a pinch of other elements, to make the metal simultaneously hard as diamond and flexible enough to withstand the vibrations of trains and wind loads from the ocean. Steel arrives at the plant as massive slabs. Some are 6 or even 8 inches thick. These are monolithic steel plates. First step, cutting. Regular saws don't work here. Giant computer-controlled plasma or laser cutting tables are used instead. You see a blinding blue flame slice through the steel slab as easily as a hot knife cuts through butter. The screech of metal is so loud, the windows vibrate for blocks around. Each piece of the future beam is cut with surgical precision. Once the parts are ready, they're assembled into a single structure. A truss is a complex geometric network of top and bottom chords and diagonal braces. The assembly shop is where bridge cranes rule. Parts weighing 10 to 15 tons get hoisted and positioned on special jigs. Welders use magnetic clamps and hydraulic presses to bring the plate edges together. Each joint gets locked with temporary welds, tack welds. At this stage, the beam already looks imposing, but it's still fragile. Welding is the longest phase. For plates this thick, they use submerged arc welding. A massive manipulator crawls along the seam, burying it under special powder while an electric arc burns inside. This prevents metal spatter and keeps oxygen out of the weld. The weld seam on a 100-ton beam can run several inches thick and consist of 30 or 40 layers of metal. That takes days, but subscribing to this channel takes less than a second. Have you made that one click yet? The temperature in the welding zone is so high that the metal glows cherry red. You can smell that dry, stinging scent of ozone and molten flux. When the beam is ready, it goes through a medical examination. Not a single weld is taken on faith. Non-destructive testing specialists scan every inch of welding with ultrasonic sensors. They're searching for microscopic air bubbles or slag inclusions. If they find any, the weld gets cut out and rewelded from scratch. Hudson Yards safety accepts no compromise. The final step, corrosion protection. The beam is shot blasted to a shine, then coated with multiple layers of specialized epoxy enamel. The color is usually gray or red. Then comes the toughest part, delivery. The beam won't fit on a regular flatbed. It's hauled on special multi-axle trailers where each wheel can pivot independently. The route to New York is calculated months in advance. Will the bridge hold? Will the trailer clear the overpass? Getting a single 100-ton beam to the construction site cost $50,000 to $70,000 in transportation alone. The route from Virginia to New York took several days. Every bridge along the way was checked to see if it could handle such a concentrated load. When the trailer rolled onto Manhattan, police shut down entire blocks because the turning radius of that beast required the full width of the avenue. Houston, Texas, high noon. The sun here doesn't just shine. It presses down on your shoulders like a heavy, hot blanket. The air above the scorching asphalt shimmers with heat waves, and your lungs fill with a thick, distinct smell. A mix of heated rubber, dry prairie, and diesel fuel. I'm standing at the gates of the Jinan plant, the world's largest tire recycling facility, and I can feel the soles of my boots starting to soften on the blistering Texas ground. Today, I'm not just a tourist. I'm a witness to a massive technological alchemical process where what the world considers waste that won't decompose gets transformed into energy and the very foundation of the highways we drive on. Houston didn't just greet me with sunshine, it slammed me with a wall of sticky heat that folks down here in Texas call the devil's breath. But the second I stepped through the entrance to Janan's facility, the sounds of the city, distant highway hum and rustling wind, instantly shifted into something far harsher. Industrial chaos. But chaos that's perfectly ordered, rhythmic, almost primal. The first thing that hits you isn't the sound, it's the vibration. You don't just hear it. It rattles your chest like a low bass line at a rock concert. That's the giant motors firing up the heart of the plant. And spread out before me are the real black Himalayas. Thousands, maybe tens of thousands of used tires stacked into neat but staggering mountains. Everything's here. Thin wheels from compacts that only ever touched smooth asphalt, all the way up to massive donuts from mining dump trucks, treads tall as a person. They all came here to die, so they could be born again. The smell here is something else. It's not just the stench of rubber. It's a complex cocktail of heated polymer, traces of road tar baked into the treads, and hot metal. The Texas sun mercilessly scorches these black surfaces, and the heat radiating off them makes you feel like you're standing next to an open oven. The air between the mountains has solidified. It's thick and oily. I watch as another truck rolls up. The hydraulics groan as the bed lifts, and hundreds of tires tumble down with a muffled rumble. Thump, 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 cascading to the foot of the black mountain. This sound of rubber hitting rubber layers over that same endless vibration from the plant's engines. It creates this uncanny sensation of being inside a living organism. The plant breathes with this rhythm. It's hungry, and these mountains are its food. The vibration intensifies when the feed conveyors kick on. You see these massive manipulators, like the claws of prehistoric monsters, tearing into the piles, snatching their prey. In this place, on the edge between old junk and raw material, you feel tiny. We're following the conveyor belt that leads straight into the heart of the main floor. Here, that vibration I mentioned earlier transforms into physical force, pounding against your eardrums. We approach it, the primary shredder. If those mountains of tires were a graveyard, then this machine is the industrial meat grinder that knows no mercy. The first thing that hits you is the contrast between speed and power. You'd expect the shredder to spin at breakneck speed, flinging chunks of rubber in every direction like a blender. But no, the shredder's shafts move slowly, almost lazily. But within that slowness lies colossal torque, force capable of crushing stone. It's a deliberately engineered method. Low rotational speed prevents the rubber from overheating, keeping it from melting and sticking to the blades, which would turn the machine into a gummy trap. When the next tire, say a massive wheel from a Texas pickup, hits the rollers, something happens that makes you flinch. The tire tries to hold its shape. Its steel belt, that same skeleton that carried tons of weight on the road, puts up one last fight. But hardened blades made from special alloy dig into the tread like the teeth of a prehistoric predator. 1 second, and you hear that distinctive crunch as the steel wires inside the rubber snap under hundreds of tons of pressure. In that moment, bright, angry showers of sparks fly out of the shredder's jaws. It's the friction of the steel belt against the blades, creating miniature lightning bolts inside the machine's dark belly. The heat here becomes almost unbearable. If it was just hot outside in Houston, near the shredder, the air heats up to a temperature where the sweat on your forehead instantly turns sticky with rubber dust. You can smell the frictional heat, sharp, metallic, with notes of burnt sulfur. It's the smell of matter being physically destroyed. Dust is everywhere here. It's not just floating in the air, it's dancing in the beams of industrial lights, settling on every surface like black velvet. These are tiny rubber particles released during the tearing process. You can see chunks falling from beneath the rollers onto the exit conveyor. This isn't a tire anymore. These are shapeless, torn scraps of rubber, roughly the size of an adult man's palm. Mangled strands of steel wire stick out from them. Those same cord fangs that magnets will pull out in the next stage. The chunks of shredded rubber that just passed through the shredder's jaws move along on the conveyor belt. They look terrible, torn, dirty, hot, with those same mangled steel wire threads, cord fangs, sticking out from every black edge. Right now, one of the most cinematic stages at the Jinan plant begins. We're approaching the magnetic separation zone. Above the conveyor, where chunks of tires race by in an endless stream, massive blocks hang suspended. Overhead electromagnetic separators. They hang low, almost touching the black flow, humming with voltage. What happens on the belt resembles an uprising of the dead. When a ragged chunk of rubber enters the magnet's zone, the steel threads inside it react instantly. You see it with your own eyes. Metal wire that a second ago was part of a solid framework suddenly comes alive. With savage force, it tears free from its rubber prison, dragging the entire chunk with it, or simply slipping out like a knife through butter. Metal literally shoots upward, defying gravity. It looks like strange, aggressive magic. Thousands of steel needles and twisted wires slam into the magnetic belt with a loud crash, spinning perpendicular to the main conveyor. This is that endless clacking, the sound of thousands of metal fragments hammering into the separator's steel armor. The heat in this zone is unique. The magnets consume a massive amount of electricity and generate heat themselves, mixing with the warmth from freshly cut rubber. You're standing in a cloud of a specific smell, a blend of ozone, which always accompanies powerful electromagnets, and warm, raw metal. It's the smell of a forge, but without fire. Look to the left of the main conveyor. Another mountain is growing there, a mountain of pure steel. The magnetic belt carries the captured metal beyond the rubber stream, and, where the magnetic field vanishes, dumps it into a separate hopper. You're looking at springs coiled into spirals, long sharp needles, tiny metal chips. Everything gleams under the factory lights with a cold, bluish glow, contrasting sharply against the matte black of the rubber. Stripped of its steel skeleton, the rubber moves forward into the darkest and most airtight section of the plant. Now that the metal's gone, the rubber chunks look surprisingly light, but that's just an illusion before the final battle. We're entering the secondary granulation zone. High-speed granulators transform the torn pieces into perfect rubber crumb. The air here is thick with black snow, fine dust swirling through beams of light. Each granule passes through a system of vibrating screens, where they're sorted by size down to a fraction of an inch. But the real climax lies ahead, inside the sealed steel pyrolysis reactors. We approach the long, insulation-wrapped cylinders. This is the zone of quiet energy. There's no open flame here, but inside, hellish heat reigns, 850 degrees Fahrenheit. The key secret? Total absence of oxygen. The rubber doesn't burn, it distills. Every year, thousands of tons of valuable timber around the world get turned into shavings, and only a few pounds become works of art. Picture this. An 11-pound block disappears in 10 minutes, giving birth to an object lighter than your smartphone. But what actually happens in that moment on the lathe? Why does a single mistake, 1 millimeter off, destroy months of work? And why are some species of wood more expensive than gold, unfazed by water, fire, or time? Today, we're diving inside a process where speeds hit thousands of RPM, and wood behaves like metal. Stick around till the end, and you'll discover the secret behind why these materials sing in music, last for centuries, and why craftsmen work with them almost like living beings. The lathe is simple genius. The blank mounts between centers or in steadies, spinning from 50 to 2,000 revolutions per minute, while high-carbon steel or carbide cutters strip away the excess. The craftsman holds the tool in hand, controlling pressure and angle. 1 millimeter off, and everything goes sideways. The process starts with rough turning. The lathe eats wood layer by layer, revealing texture, color, shine. Shavings fly like confetti, filling the workshop with the scent of fresh bark. First, the roughing gouge cuts the diameter down to shape. Then the bowl gouge forms the vessel, and the finishing tool polishes to a mirror finish. The speed is stunning. From an 11-pound blank, in 10 minutes, you get a piece weighing 2.5 ounces. Finish with oil or wax. The wood glows. Not every tree works for the lathe. You need species with uniform grain, no knots, no cracks. Rosewood, or palisander, the king of exotic lumber, hailing from the tropical forests of India, Brazil, and Madagascar. Its heartwood stuns with a violet-red hue that darkens over the years into a rich wine color with black and gold streaks, like a marbled masterpiece of nature. The surface feels oily to the touch. The wood is saturated with resins, which make it gleam like a polished ruby and give off a subtle sweet rose fragrance that lingers in the workshop for hours. Its physical properties make rosewood a turner's dream. Density of 53 pounds per cubic foot, Brinell hardness of 5.5, 3 times harder than oak, yet flexible as bamboo. On the lathe, it cuts like butter. Shavings fly off in thin ribbons, won't clog the blade, won't crack from centrifugal force. The fibers are elastic, so bowls with walls just 1/10 of an inch thick don't split, and candlestick stems survive drops from 3 feet up. The natural oils protect against fungi, beetles, and moisture. Pieces last centuries without varnish. From rosewood, craftsmen make whiskey tumblers for you. The shape is graceful, walls thin enough to see the drink through. The wood's aroma enhances those oak notes. From Indian rosewood, they make sushi sets. Boards, spoons, holders. The contrast of red with white rice looks refined. Often combined with other woods, rosewood plus olive equals a vase with double shimmer. Gibson Les Paul guitars have rosewood fingerboards. The sound is warm, sustained, with deep bass. Stradivarius violins featured rosewood fittings. Today, it's used for saxophone and flute mouthpieces. The material resonates across all frequencies. Rosewood veneers go onto yachts, Steinway pianos, palace tables. The hardness allows polishing to a mirror finish. An unvarnished surface looks like lacquered obsidian. Working it demands skill. Dry in shade for months, because sun exposure causes cracking. Cut with sharp carbide blades. Dull ones bog down in the resins. Final touch, linseed oil or carnauba wax, which brings out the purple undertones. Heat treatment makes the wood fire resistant and nearly black. Red sandalwood, a sacred exotic species from the tropical forests of southern India and Sri Lanka, valued higher than gold thanks to its unique red coloration and magical properties. The heartwood has a rich garnet red color that, when soaked with water or oil, takes on a blood red hue, like a genuine ruby embedded in wood. The surface is smooth, with a subtle sweet aroma reminiscent of vanilla and rosewood. This scent lingers for years, filling spaces with the warmth of the East. Its physical properties make it a turner's dream. Density of 69 pounds per cubic foot, heavier than oak or rosewood, high hardness, but flexible fibers that allow creating thin-walled pieces without cracking. On the lathe, it cuts slowly, demanding sharp carbide tools. The shavings come out fine and red, like brick dust. The oiliness is natural, so finishing oil just enhances the inherent luster, making the surface look like polished garnet. Best for premium tableware and ceremonial pieces. Turners craft bowls for Ayurvedic ceremonies from red sandalwood. The red color symbolizes Kundalini energy, and the wood absorbs meditation vibrations. Chalices for sacred drinks hold their shape for centuries without picking up odors. In Japan, they carve bonsai stands and teaspoons from it. The contrast of red against white porcelain is stunning. Sushi knife handles are status accessories running hundreds of dollars. Red sandalwood is beloved by masters of the bamboo flute tradition, where the tone comes out soft yet deep. Guitars with red sandalwood fretboards sound warm, with exotic overtones. In India, they make mridangams from it, drums for temple rituals, where the wood's vibrations amplify the meditative effect. Buddhist prayer beads, Hindu jewelry, ritual cups, Red sandalwood is considered a conductor of spiritual energy. In Tibet, they carve prayer wheels from it. In Japan, tea ceremony spoons. Veneers go into premium furniture for yachts and palaces. The wood doesn't fear salt water or heat. Processing demands ritual. Dried in darkness for 2 years. In light, the red fades. Cut slowly with sharp tools, the dust is toxic. Work in masks. The finish, natural sandalwood oil or carnauba wax. Heat treatment at 300 degrees makes it black-red, fire-resistant. Turning isn't just about shaping. Masters combine techniques. Roughing cut. They remove bulk, reveal the shape. Deep hollowing, for bowls, goblets, where the tool bites deep, creating walls 2 millimeters thick. Taper turning, for graceful candlestick stems. Final sanding, grit from 40 to 2000, then oil for shine and protection. Pros add segmented turning. They join rings of different species, like a puzzle. A vase from 10 types of wood. Or texturing. Carving patterns with the tool that come alive when spinning. Heat treatment. Wood heated to 400 degrees Fahrenheit, making it fire-resistant and darker. African blackwood ebony. The darkest treasure of the tropical forests of Cameroon, Ghana, and Nigeria, where it grows slowly, accumulating resinous blackness in its heartwood over years. The wood looks like polished obsidian, deep black with gray or brown veins creating a midnight marble effect. The surface is smooth as glass with a natural metallic sheen. Ebony is so oil-saturated it needs zero varnish. The scent is subtle, earthy, with smoky notes that linger in the workshop for hours. The physics is wild. Density 75 to 80 pounds per cubic foot. This wood sinks. Brinell hardness of 8, twice as hard as oak. On the lathe, it behaves like metal. A sharp carbide tool peels off shavings in thin black ribbons. No vibration, no tear out. Centrifugal force doesn't break the fibers. They're springy like steel cable. Bowl walls a 1/16 of an inch thick don't crack. Stems hold multiple pounds. The oiliness makes ebony indestructible. It won't rot, resists termites, heat, and salt water. Turning artistry at the edge of what's possible. From Cameroonian ebony, craftsmen make spheres just over an inch in diameter with diamond-like facets. Perfect shine without polishing. Sake or whiskey cups. Status minimalism. Black contrasts with clear liquid. Japanese knife handles. Eternal, don't slip in hand. Don't dull the blade. Often combined with silver or mother of pearl, ebony emphasizes the whiteness of the inlays. Musical instruments. Legendary. Flutes, saxophone mouthpieces, double bass fingerboards, sound pure as crystal, without parasitic resonances. Ebony clarinet mouthpieces cost thousands of dollars. The material doesn't absorb moisture from the air. In Japan, they make kozue from it, bamboo inserts for flutes. Rings, bracelets, pendants. Ebony's harder than bone, polishes to a mirror shine. Veneers for yachts, palaces, Patek Philippe watches. Ebony flooring, an eternal investment, never fades, never chips. Working it, that's where the master gets tested. Dried 3 years in darkness, light dulls it. Cut slow, a dull blade gums up in the resins. Dust is toxic, masks mandatory. Finish with carnauba wax or tung oil for that wet gloss. Heat treatment at 400 degrees turns it blue-black. Every year, deep within the planet, a process unfolds without which the modern world would simply fall apart. A metal almost no one talks about determines the fate of reactors, skyscrapers, and engines operating at the edge of possibility. It's extracted where the air is thin, in quarries deeper than skyscrapers, and most of this substance never reaches human hands in pure form. Why do nations compete for deposits where this metal's content is merely fractions of a percent? How does a gray rock give birth to an alloy that withstands hellish temperatures? And most importantly, why wouldn't super strong steel exist without it? Stay until the end, and you'll discover the hidden role of molybdenum that even textbooks don't tell you about. The world's largest molybdenum reserves are concentrated in complex deposits where molybdenum is closely associated with copper, forming joint mineral formations. These deposits form under special geological conditions, and the world's leading countries control their extraction, ensuring the global supply of this strategic metal. Chile holds first place in global molybdenum production thanks to the giant Chuquicamata deposit, considered one of the largest on the planet. Located in the Atacama Desert, at an elevation of over 9,000 feet above sea level, this deposit is a true legend of mining. Here, molybdenum is extracted as a byproduct during copper ore mining. From each ton of copper ore, about 45 pounds of molybdenum concentrate is produced. Annual output exceeds 30,000 tons of pure molybdenum, making Chile the supplier of 30% of the global market. Operations are conducted in an open-pit mine 1,200 feet in diameter and half a mile deep, where giant excavators and conveyor systems are used to transport the ore. In the United States, the key site is the legendary Climax deposit in Colorado, which provides about 20% of global molybdenum production. This unique geological wonder of the San Juan Mountains contains billions of tons of ore with molybdenum concentrations up to 0.3%. Extraction here began back in the 1920s, and today the Climax pit is one of the largest in the world. Its area reaches 2,500 acres, and its depth is nearly 2,000 feet. Freeport-McMoRan is investing billions in modernization, using automated systems and green technologies to cut emissions. From here comes high-grade concentrate that's exported to Europe and Asia. China and Peru are also aggressively developing their deposits. In China, the leading sites are in Henan and Shanxi provinces, where they mine over 80,000 tons annually. And in Peru, the massive new Racio de Alto deposit promises to become one of the largest. Here, molybdenum is extracted alongside copper at depths reaching 6,500 feet using underground mines. The project, run by Southern Copper, involves $2 billion in investment and projected output of 20,000 tons of molybdenum per year starting in 2025. The uniqueness of these deposits comes down to geological processes. Molybdenum crystallizes in porphyry copper ores under the influence of magmatic hotspots, zones where molten magma penetrates the Earth's crust, enriching the rock with metals. Ore is extracted through open-pit mining at surface deposits or underground methods in deep mines, where drill rigs and blasting operations are used. After crushing, the rock is enriched through flotation, a chemical process where molybdenum minerals are separated from waste rock, yielding a concentrate with a metal content of 45 to 50%. This stage is critically important because it determines the efficiency of subsequent processing. These deposits don't just supply raw materials for metallurgy, they drive the development of extraction technologies in extreme conditions, from desert quarries to high-altitude mines. The molybdenum from them becomes the foundation for ultra-strong alloys that are transforming industry. The production process for ferromolybdenum starts with molybdenum ore arriving at the plant as large chunks of rock from the deposit. First, the ore gets loaded into powerful crushers, giant mechanisms that look like massive jaws, breaking the rock down into fist-sized fragments. Rumbling and dust fill the air as hammer or cone crushers convert tons of ore into fine particles. Next, the crushed ore feeds into mills, cylindrical drums about 10 yards long, filled with steel balls. They spin, grinding the rock into powder. From here, the mass flows to processing plants where flotation happens. Foam is added to large vats of water and reagents. Molybdenite sticks to the bubbles and floats to the surface like froth, which is scraped off. The rest settles as waste. The resulting concentrate, a moist gray powder, is dried in rotary kilns at temperatures near 600 degrees Fahrenheit, transforming it into a finished product for smelting. This stage takes hours, but determines the quality of the entire chain. After roasting, the molybdenum concentrate transforms into pure molybdenum trioxide, a yellow powder ready for final transformation into ferromolybdenum. This stage is the heart of production, where electric arc or aluminothermic furnaces transform iron and molybdenum oxide into a charge that's then carefully refined. The process demands extreme temperatures, precise control, and heavy-duty equipment, because molybdenum melts at a whopping 8,587 degrees. Electric arc melting is the go-to method in modern plants. Massive electric furnaces, with capacities from 10 to 50 tons, are loaded with the charge. Graphite electrodes 40 inches in diameter create an arc with 300 to 500 watts of voltage, heating the mass to nearly 11,000 degrees. In this scorching plasma, the oxide breaks down. Aluminum surrenders its oxygen to slag, while the iron molybdenum melts into an alloy. The reaction is violent. Sparks, flames, the furnace roaring. Slag floats to the surface and gets tapped off by crane. Melting happens in vacuum or argon chambers to prevent oxidation. Aluminothermic smelting, an older but effective method for small batches. In reaction crucibles, they mix molybdenum with aluminum powder and iron, then ignite it with a magnesium ribbon. The exothermic reaction instantly heats the mixture to the required temperature, reducing the metal in 5 or 10 minutes. Slag is removed mechanically. This method is cheaper but less pure. The resulting charge is refined, purged with argon to remove gases. Flux is added to clean out impurities. Spectrograph analysis monitors composition every 15 minutes. Refining takes 1 to 2 hours, bringing purity up to 99.5%. The finished ferromolybdenum, a silvery melt, is poured into molds for briquettes weighing 2 to 110 pounds. On the conveyor lines, the molten metal pours into steel or cast iron molds, cools under water spray for about 20 minutes. The briquettes get crushed by vibrating hammers, sorted with magnets, and packed into 2-ton barrels. The surface is shiny, pore-free, ready to ship. Ferromolybdenum in those 2-ton briquettes, it's the secret ingredient for steelmakers, because without it, you can't make ultra-strong steel that'll survive the hell of industry. It gets shipped to electric steelmaking plants all over the world: China, the US, Europe, Turkey, India. There they crack open the briquettes, load them into converters or electric furnaces, along with iron and coal. Molybdenum makes the steel uniform, heat-resistant, corrosion-resistant, prevents overheating. At the steel mill, ferromolybdenum briquettes arrive in hoppers or containers and head straight to the breaking station. Workers in protective gear use hydraulic hammers or vibrating breakers to crush them into 2 or 4-inch chunks. The sharp crack of metal echoes through the shop floor, dust settling under the ventilation system. The broken fragments get weighed and sent via conveyor belt to the scales. Next comes loading into converters or electric arc furnaces. The converter, a giant 200-ton vessel, gets filled first with molten pig iron from the blast furnace. Then cranes dump in scrap iron, coal powder for carburization, and batches of ferromolybdenum. The molybdenum dissolves instantly, forming molybdenum carbides that stabilize the structure. In an electric furnace, the process is similar but more precise. An arc from graphite electrodes melts the charge. Ferromolybdenum is added in portions through a hatch. Oxygen is blown through for refining. Gases are vented. Molybdenum makes steel uniform, heat-resistant, corrosion-resistant, and resistant to overheating. No cracks under pressure. The molten metal is poured into a crystallizer, where finished steel comes out. The shop roars, sparks fly. Real industrial action. Every hour, millions of metal parts are born around the world that have never seen the inside of a smelting furnace. They're not cast, not machined from bar stock, and not forged with a hammer. So what is this metal that starts out looking like powder, then goes on to withstand the loads of a jet engine? Powder metallurgy, a quiet technology working behind the scenes of the modern world. In your smartphone, your car, hospitals, and even in space. It saves up to 70% of material, creates shapes impossible for traditional manufacturing, and changes the very logic of metal itself. But there's one moment almost nobody talks about. The process where the metal isn't solid yet and is no longer powder. Stick around to the end, and you'll find out why it's precisely in this phase that the fate of strength, lifespan, and cost of the future part is decided. From the gears in your phone to jet engine parts, from surgical instruments doctors use in operations to car components, powder metallurgy is everywhere. It's a technology few people hear about, but without it, the modern world would look completely different. Let's break down how it works and why it's so awesome. Start at the very beginning. Metal powder. These are specially manufactured particles ranging from 1 to 100 micrometers in size. For comparison, a human hair is about 70 micrometers thick, meaning these particles are so tiny that if you pour them into your palm, they feel like velvet or face powder. Under a microscope, each particle looks like a tiny sphere or an irregular shape with a smooth surface. There are several ways to make this powder. The most popular? Atomizing molten metal. A stream of liquid metal at temperatures around 3000 degrees Fahrenheit gets blasted under enormous pressure by jets of water or gas. The metal instantly shatters into millions of tiny droplets that freeze in mid-air as they fall. What you get is a fine powder with particles that are almost perfectly spherical. Another method? Electrolysis. Metal deposits from a solution onto electrodes as fine particles, which are then collected and dried. This method produces very pure powder, but it's pricier. Then there's mechanical grinding in ball mills, where metal is simply pounded by heavy balls until it turns into powder. But these particles come out irregular with sharp edges, which isn't always ideal for further processing. Each metal needs its own approach. Iron, stainless steel, copper, aluminum, titanium, tungsten. They all become powder differently. You can also mix powders from different metals to create alloys with unique properties that are difficult or impossible to achieve using traditional methods. Now here's where it gets interesting. What do you do with this powder? Step 1. Mixing and prep. You add various substances to the metal powder. Lubricants so the particles slide past each other more easily, binding agents that hold them together, sometimes graphite or other additives to improve properties. All of this gets thoroughly mixed in special mixers, so every single particle is coated with the right additives. Next comes pressing. The prepared mixture gets poured into a mold called a die. This die is made from super hard steel and has the exact geometry of the final part. Powerful presses squeeze the powder from above and below, creating pressure from 15 to 60 tons per square inch. That's like stacking several elephants on an area the size of your fingernail. Under that pressure, the powder particles compress, deform, and lock together mechanically. The air between them escapes, and the powder transforms into a dense blank that actually holds its shape. This is called a green compact, or green body, though it has nothing to do with color. Just the term. It's still pretty fragile and crumbles easily if you're not careful, because the particles are only held together by mechanical interlocking and adhesive additives. The green compacts get loaded into special furnaces, where they're heated to temperatures ranging from 1600 to 2300 degrees Fahrenheit, depending on the metal. That's below the metal's melting point, but hot enough to get the atoms moving and diffusing between particles. Something remarkable happens inside that furnace. Metal atoms on the particle surfaces start migrating, jumping from one particle to another, filling voids, creating strong metallurgical bonds. The boundaries between individual particles gradually dissolve, and the powder transforms into a solid, monolithic material. The part shrinks, becomes denser. It can lose up to 20% of its volume. The entire sintering process takes several hours and happens in a controlled atmosphere. Typically, you use inert gases like nitrogen or argon, or even hydrogen, to prevent the metal from oxidizing at high temperatures. If you allow contact with oxygen, the part will develop an oxide film and lose its strength. After sintering, the part is cooled slowly. Cooling it too fast can create internal stresses and cracks. And here's where the final magic happens. The part acquires its ultimate properties. The metal's microstructure forms, grains grow, internal stresses are relieved. What do you end up with? A part with a density of around 90 to 95% of cast metal. That means there are still some pores inside, tiny voids just a few micrometers in size. But this isn't a flaw, and sometimes it's actually an advantage. These pores can hold lubricant, making the part self-lubricating or absorb vibrations and sound. These parts are often stronger than cast equivalents. Why? Because the microstructure turns out fine-grained and uniform. No large crystals that could be weak spots. No segregation or inconsistencies that happen during casting. The metal is distributed evenly, and impurities, if any, are also distributed perfectly. For some applications, you need maximum density with zero porosity. That's when additional processes come in. Hot isostatic pressing. The part is reheated and compressed with gas under pressure up to 10 tons per square inch from all sides simultaneously. Pores collapse, and density reaches nearly 100%. Or you can use powder forging. The sintered blank is heated and forged, just like regular metal. You end up with a part that has properties impossible to achieve any other way. Super strong, ultra dense, with precise dimensions. The beauty of powder metallurgy is that you can make complex shaped parts with virtually zero waste. With traditional machining, you cut the desired shape out of a metal block, and up to 70% of the material ends up as chips. Here, the powder is poured precisely into the mold of the future part, sintered, and that's it, minimal scrap. After sintering, parts often require minimal additional machining or none at all. Dimensions hold to within a few hundredths of a millimeter. For comparison, a sheet of paper is about 100 micrometers thick, and powder part precision can be 10 times better. You can create gradient materials, where different parts of a single component have different compositions and properties. For example, a gear where the teeth are made from hard, wear-resistant alloy, while the core is made from softer, tougher metal that won't break under load. You can't do this with casting or machining. Powder metallurgy lets you work with metals that are tough to process traditionally. Tungsten melts at over 6,000 degrees Fahrenheit. Try casting that in a regular furnace. But with powder, you can easily make tungsten contacts for electronics or crucibles for melting other metals. Titanium, strong as steel, light as aluminum, but incredibly expensive to machine because it's chemically reactive and abrasive. Powder metallurgy makes titanium parts economically viable. That's why it's used for medical implants, artificial joints, dental implants, bone plates. In the automotive industry, powder metallurgy is the standard for gears, bearings, piston rings, valves. A single modern car contains up to 110 pounds of parts made by this method. They're cheaper, lighter, and more reliable than traditional ones. In aerospace, powders are used to make turbine blades that withstand temperatures over 3,600 degrees Fahrenheit and spin at over 10,000 revolutions per minute. Composite materials from particles of different metals and ceramics deliver properties impossible for conventional alloys. 3D metal printing is exploding right now. It's basically powder metallurgy, but instead of pressing, you lay down thin layers of powder and fuse them with a laser or electron beam, one layer at a time. You can create parts so complex, they're impossible to make any other way. Hollow structures, internal channels, lattice frameworks. Picture an industrial world where you need to shape and size the toughest materials. Think hardened steel or high-strength alloys. To drill, mill, or cut one metal, the cutting tool itself must be made from a material with extreme hardness, far exceeding the part being worked. In this battle for dominance over material strength, the invisible but indispensable hero is tungsten carbide tooling. Without these materials, the modern precision, speed, and efficiency of the machine building industry would be impossible, from manufacturing aircraft engines to producing the tiniest electronic components. If you're searching for the foundation to build a tool capable of outperforming any other, you need to start with this element. Tungsten occupies a unique position where its physical properties simply have no equal. Meet the main superpower: heat resistance. Tungsten is the absolute unshakable champion among all known metals for melting point. Picture this: its melting point reaches a phenomenal 6,192 degrees Fahrenheit. To put that scale in perspective, iron, considered strong and refractory, already melts at a temperature barely exceeding 2,700 degrees. This extreme temperature resistance is direct proof of the extraordinary strength of its internal atomic bonds. Tungsten simply refuses to surrender to heat, making it irreplaceable for tools operating under extremely high thermal stress. But its advantages go way beyond just temperature. Tungsten is the perfect material for tooling work, thanks to two other key characteristics. First, incredible density. It's extraordinarily heavy, almost 1.7 times denser than lead. This mass, built into a cutting tool, provides the necessary inertia and stability, even at dizzying cutting speeds. A tool made from it doesn't vibrate or deflect, guaranteeing surgical precision. Second, geometric reliability. Tungsten has a minimal coefficient of thermal expansion. This means that when a cutter or drill heats up to hundreds of degrees during metal machining, it maintains its geometric form with micron-level accuracy. Zero creep or deformation. This stability is a critical condition for precision engineering. But there's one catch. Pure tungsten on its own, while refractory and dense, just isn't hard enough. And worse, it's prone to brittleness for direct use as a cutting tool. Its potential only fully unleashes when it transforms into its superhero form. Its true, unmatched power is released when it enters a powerful chemical reaction with carbon, forming the legendary tungsten carbide. This is a ceramic material produced by heating a mixture of tungsten and carbon powders to high temperatures. Tungsten carbide's structure is characterized by covalent bonds, which are far stronger than typical metallic ones. These tungsten carbide crystals are among the hardest known materials on the planet. Their hardness on the Vickers scale exceeds 2500 HV, falling just slightly short of diamond, which clocks in at 10,000 HV, and cubic boron nitride. Compared to the hardest hardened steel, tungsten carbide is roughly twice as hard. Although tungsten carbide is incredibly hard, it's also very brittle, similar to ceramic. If you used pure tungsten carbide for a cutting tool, it would simply crack during the first impact load or vibration. To eliminate this brittleness and give the material the necessary toughness, meaning the ability to absorb impact energy without failing, a metallic binder phase is used, most commonly cobalt. How do you create a material that only melts at 6,000 degrees Fahrenheit into the form of a perfectly precise tool? The answer is simple. Conventional casting doesn't stand a chance. Tungsten carbide is too stubborn and won't yield to standard industrial furnaces. So to create these cutting titans, inserts, end mills, drill bits, you need high-tech engineering wizardry, powder metallurgy. First, we take two key ingredients: ultra-fine tungsten carbide powder, which is our super hard foundation, and cobalt powder, our future cement and shock absorber. They're carefully mixed in a precise proportion. Balance is critical here. Less cobalt gives maximum hardness, but brittleness. More cobalt makes the tool tougher and more impact resistant, though slightly less hard. After mixing, the blend is pressed under colossal pressure, forming perfectly precise blanks for inserts or drill bits. It's like creating a raw, not yet fired, but already shaped product. But the real transformation happens in special vacuum or hydrogen furnaces during a process called sintering. The temperature slowly but steadily climbs until it exceeds a critical point. At that moment, cobalt, being the more accommodating metal, melts. Meanwhile, the super hard tungsten carbide crystals remain completely unmelted. This is liquid phase sintering. Molten cobalt, like a river, floods every gap between tungsten grains. It acts as a binding agent, tightly enveloping each super hard grain. The structure takes on the appearance of a perfect brick wall, where tungsten grains are the bricks and cobalt is the mortar. After cooling, we get a cemented carbide that demonstrates phenomenal synergy. It has hardness comparable to diamond, but thanks to the cobalt matrix, it has enough strength and toughness to withstand the impacts and vibrations that are inevitable during cutting. It's this perfect combination that allows these unassuming tools to cut even the toughest hardened steel and exotic alloys without any noticeable wear. Tungsten carbide tooling is so critical that roughly 50% of all tungsten mined in the world goes into making it. This underscores its strategic importance to the global economy and industry. The applications of these unsung heroes span virtually every industry that requires metalworking. Milling cutters, lathe tools, drill bits, and reamers with carbide inserts form the backbone for manufacturing engine blocks, transmissions, turbines, and other high-precision components. They allow cutting at high speeds, dramatically boosting productivity. Mining and extraction. Drill bits and inserts for mining equipment, built on tungsten carbide, are essential for penetrating the hardest rock formations and granite. No modern mining or oil and gas drilling operation is possible without this technology. Machining titanium and heat-resistant nickel alloys, used in turbine blades, demands tools that can withstand extreme temperatures and chemical interaction. Carbide tools, often with additional coatings like titanium nitride, are the only practical solution. Tungsten carbides are used to create dies for stamping, wire drawing dies for wire production, and wear-resistant components in pumps and valves where abrasion resistance is essential. The total value of the global market for tungsten carbide-based hard alloys and tools made from them is estimated at tens of billions of dollars annually. This is a high-margin industry, critically important for manufacturing, because quality tooling, while expensive, pays for itself many times over through increased machining speed and precision. The service life of a cutting carbide insert can be extraordinarily long. In some cases, an insert can machine several tons of material before it needs replacement or resharpening. This far exceeds high-speed steel, which requires frequent replacement. Tungsten is a strategic and relatively rare metal, making its recycling vitally important. According to estimates, a significant percentage, sometimes as much as 30%, of the tungsten used in manufacturing new hard alloys comes from recycled worn-out tools. This saves energy and reduces dependence on primary ore extraction. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would stop, lights would go dark, and space engines would fall silent. And yet, it's so rare that the entire world fights over every single gram. But here's the real kicker. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that'll flip your understanding of the metal-holding civilization together. Tungsten is a true engineering phenomenon. Its unique properties let us push the boundaries of what's possible in technology, from deep underground to the heights of space. Its story, a story of endurance and unmatched strength. Tungsten is element 74 on the periodic table, one of the transition metals. It has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. To put that in perspective, that's a temperature where most other metals would have vaporized long ago. On top of that, tungsten has the highest tensile strength of any pure metal, at temperatures above 3,000 degrees Fahrenheit. It's incredibly hard and dense, making it irreplaceable for applications demanding maximum resistance to wear, deformation, and extreme temperatures. Tungsten doesn't occur in pure form. It's extracted from ores, with the most common being wolframite and scheelite. Wolframite is a complex compound of iron, manganese, and tungsten, while scheelite is calcium tungstate. These ores, hidden deep in the Earth's crust, are the raw material for all subsequent industrial processing. The world's major tungsten producers include countries like Vietnam, China, Russia, and Canada, which hold significant reserves of this strategic metal. The tungsten extraction process is a complex sequence of mining and metallurgical operations. It starts with exploration and ore extraction from underground mines or open-pit quarries. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep within the earth. It's tough, dangerous work that demands cutting-edge technology and strict safety standards. Thousands of tons of ore are hauled to the surface every single day. After extraction, the ore heads to a processing plant. Here it goes through several stages to separate valuable wolframite or scheelite from other rock. First, the ore gets crushed in crushers and mills until it's a fine powder. Then various enrichment methods kick in: gravity separation, magnetic separation, and flotation. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The concentrate is then processed at metallurgical plants to extract pure tungsten. It's a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent roasting to produce tungsten oxide. The tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. The result is a fine tungsten powder, which forms the foundation for all subsequent products. From this powder, through sintering, tungsten rods, bars, and other blanks are formed. Tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, creating a dense, strong material. One of the most critical applications: manufacturing tungsten carbide. Some seriously tough stuff. These alloys combine tungsten with carbon, plus cobalt or nickel as a binder, creating one of the hardest man-made materials on Earth. They're used to make cutting tools, drill bits, end mills, lathe inserts that can slice through the hardest metals and alloys. Without tungsten carbides, modern manufacturing, metalworking, and oil and gas extraction would grind to a halt. A single pound of tungsten can become a drill bit capable of boring through thousands of feet of rock. Talk about efficiency. Tungsten also sees heavy use in military applications for armor-piercing rounds and bullet cores. Thanks to its extreme density and hardness, tungsten alloys have exceptional penetration characteristics, delivering devastating effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is indispensable. It's used to make filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components that need high heat resistance and electrical conductivity. Because of its sky-high melting point, it's used in the aerospace industry for parts exposed to extreme temperatures. High-temperature tungsten alloys are used in jet engines, turbines, and other devices operating under extreme heat. Alloying with tungsten boosts the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with way less toxicity. On top of that, tungsten's used to make ballasts and counterweights in race cars, aircraft, and yachts thanks to its crazy high density. It's even a component in some jewelry because of how hard it is and how resistant to scratches. Tungsten is one of the rarest elements in Earth's crust, which makes mining and producing it especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential resources that haven't been explored yet, the total volume could be significantly higher. That's obviously way less than reserves of metals like iron or aluminum, which really highlights its strategic value. Global tungsten production each year, measured in tons of pure metal, or tungsten oxide equivalent, fluctuates, but in recent years, it's been somewhere between 85,000 and 100,000 metric tons annually. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine this. You could take a worn-out tool that's already served its purpose and transform it back into something brand new, without spending the energy and resources to mine ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is one of the most advanced and efficient processes among all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number. It shows just how valuable this metal is and how much economic sense it makes. Where does used tungsten come from? The main source of secondary raw material for tungsten is, of course, worn-out carbide tools. Those same cutting tools, drill bits, milling cutters made from tungsten carbide. After heavy use, they wear down, lose their edge, or break. Instead of tossing them in the trash, they're collected and sent to recycling plants. Other sources include scrap metal containing tungsten, leftover waste from tungsten product manufacturing, plus some electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of mining ore and initial processing. Recycling dramatically reduces the environmental footprint of tungsten production. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production more green and responsible.